Okay, Larry, tell me about the main design parameters of this, just the main features, like for example, preheating the fuel, preheating the air, combustion air, things like that. Tell me some of the main features, just describing this burner, which looks like we've got here's a diagram of it. Let's see, on the computer. Was it on the computer too?
Yeah, it's on there. Let's see.
Yeah. But tell us the basic design, how that works here, with reference to this graphic that's on the wiki. You can take a look at that, examine it in more detail.
Yeah.
But so what do we have?
So we have the hopper here where the fuel is put in through the lid on the top. It's a double seal because where you have gasification, you have pyrolysis of the fuel, and it's different from the normal wood stove that blends all the processes together of gasification, combustion, and heat exchange. So you have the sealed hopper here with the fuel on it, and that can be extended up to incorporate as much fuel as you want.
Mm-hmm.
The fuel drops into with a vertical side so it can't be hung up. One of the big problems with fuel feeds and gasifiers is that they have a major constriction where the fuel bridges. This one, the fuel doesn't bridge because when it gets down to this zone, it's met with super hot air for the gasification reaction, which ignites a part of the fuel, a small part, that creates the heat, additional heat that turns it all into gas. It goes through the coal bed down at the grate area here, and that combined with the steam, which has H2O, combines with the carbon to create hydrogen and carbon monoxide, both fuels that burn super efficiently. Used to be that they had coal gasification in cities like Seattle that had pipes running all over the place with this gas from coal gasification, which is essentially the same, producer gas it creates. And they ran all the lighting and engines and stuff like that from it. Biomass creates a much cleaner gas and a much cleaner ash. So the ash then is precipitated down below the grate, which has these conical rungs that keep the fuel from falling through but allow the ash to drop in and the gas to go through. So then the gas goes up into the combustion shell, which is an annular ring around this cylindrical configuration that preheats the combustion and the gasification air. The gasification air comes up from the bottom, is heated by the shell surrounding the ash pit and the hot gases that are evolved, and then it's further heated by the combustor, the combustion shell, and it goes up, and then it starts heating the fuel inside by this ceramic shell that's the hopper shell as well. And that hot air then enters in the gasification reaction. So by having everything heated, you have a very even creation of the gas, very even combustion, and then it goes into the heat exchanger shell, which takes the heat out of it. So you have these three processes, gasification, combustion, heat exchanger, that are separated and controlled separately, so you have maximum control over the whole operation.
Tell us about the water and how it balances the combustion. With the water present, how it transfers the heat.
So the water is in the thinner shell. If you can see three shells here of the heat exchanger. These are a spiral configuration that goes. The gas has to go in this spiral configuration as it goes out. As the gas goes by the water heat exchanger shell, it heats the water as it cools and drops and ends up going out the bottom of the heat exchanger shell, while the water comes in cool at the bottom, and it goes in the spiral and comes out hot in the middle at the top.
Mm-hmm. And I was talking more about the steam,
For
how the hot steam helps the
okay,
combustion.
so you've got in the gas that is fully burned. This serves two functions. It's either a gasifier or a combustor water heater, and the gasifier will heat the water as well if you don't have combustion. But let's look at the combustion first. So you've got fully combusted gas that has essentially carbon dioxide, nitrogen from the air, and water vapor. And the water vapor has a tremendous amount of latent heat in it from turning it from water into steam.
Mm-hmm.
So you can recuperate that heat of combustion by condensing the steam into water. And the condensation process not only gives you that all the heat back that is latent in the water, so you don't have a penalty from burning green wood.
Mm-hmm.
It also scrubs the exhaust so that every fly ash particle becomes a nucleus for condensation of the rain that happens in the bottom of the heat exchanger. It's a super clean heat exchanger, and you get a gas out that has no smell, and that condenses clean water out of it.
Mm-hmm. And what about in the actual pyrolysis part, the role of steam in that part, where it transfers the heat evenly?
Yeah.
Like that part?
In the pyrolysis reaction, you have a very complex mixture of gases that, with heat, become more simplified, and with when it goes through,
Broken down.
Hmm?
I mean, broken down?
Yeah, broken down into smaller molecules, and eventually those go through the charcoal bed. Now the charcoal takes the H2O, the hydrogen and the oxygen, and breaks it down into hydrogen and carbon monoxide, which is a fuel. And it also, because steam is a bipolar molecule that absorbs and radiates radiant energy, whereas nitrogen, oxygen, hydrogen don't. They don't absorb and radiate. So you have, with steam, it spreads the heat very quickly to all of the gases, and then for combustion, it does the same thing, and it shortens the flame path. It creates a much cleaner burn. So you actually benefit from having that steam in your process.
And that steam being from combustion or from the moisture in the wood?
From both. You've got green wood can have 50% of the weight of the wood can be water, and then the dry wood, when it burns, can create over 50% water from that combustion process. So you've got a tremendous amount of latent heat available from that steam, and it also acts as a catalyst and creates a higher quality wood gas.
Mm-hmm. So that's pretty amazing that you're saying to us that with very green wood, you take no penalty on the efficiency of the burn. In fact, the water helps to do the burn when you do this properly as designed
Right.
in this.
As long as you have sufficient heat in the process, evenly distributed, which the steam contributes to, and you introduce preheated air so that the combustion is always up at a high temperature, no matter where it's coming from in the system, then you have everything is fully burned. You get proper mixing, and you get excellent efficiencies from this whole system.